here's another DOD fail. My apologies, I didn't recognize it well. All right, so what's happening? Why is this the case? Why are the solvers sort of failing? And this is not unique to Cplex. I mean, the other solvers are very similar to that. So this picture tries to sort of illustrate what's going on. You have a convex objective we're trying to minimize, but we're looking for not over the continuous domain, and it'll be easy to find a solution to that, but we're looking for a solution that is a vertex, like of this, let's say, cube, or square in this case. Okay? And the solutions that we're looking for is one of these four, right, in this case. Typically, these algorithms, what they do, what we teach in linear integer optimization is, okay, so you have some linear, some polytope, and integer points are inside somewhere, and so solve the convex relaxation, get an answer to it, and then cut it off. And resolve it, you get that solution, and cut it off. And you get that solution, cut it off. And that is, these are the type of algorithms that they do to strengthen the relaxations, and then hopefully you either have to branch if you cannot find a cutting plane, or you maybe get this vertex solution here if you have a very good cutting algorithm. Otherwise, it would branch. But it doesn't work here because the convex solution is in the center of the convex hull. Right? It is, whereas in the linear case, the convex hull, this is the convex hull. The fractional solutions to the relaxation are outside. Whereas in this case, the solution is inside because you have a convex objective.
So, Alper, I thought the objective was concave.
Objective with concave. Good. When x is, if you drop the square, it is concave. When you put the square in there, it is convex. And we need to convexify. We need to give this objective to the solvers because that's what they can use. You wouldn't be able to input.
I see. So this is just because of the solver's
yes
interface.
Yeah.
I see. Okay.
Now, what do we do to resolve this issue? We're going to go to epigraph. Right? So that is your this is your function we're trying to minimize. That is your optimal solution to convex relaxation. It is not a boundary point, right? So we go to, if we go to the epigraph. Now this is your feasible region, and that is your optimal solution, and it's a boundary point, it's an extreme point, and we can cut it off with linear cuts, whereas we couldn't do otherwise. So you can add this inequality. Once you add that inequality, you minimize again. That's going to be your integer solution. You're done. Okay? So we need to go to the epigraph. Now we can do this in general for any set function. So let h be some real valued set function, and suppose we want to minimize it. Instead of that minimization, I can do this minimization over the convex lower envelope. So if I could find the convex lower envelope of this discrete function, then I could just minimize z and then do the optimization over that set. But it is difficult to find in general the convex lower envelope of an arbitrary set function. It is challenging. Okay. Now, there is a special case where it is not that challenging, and that is when h is a submodular function. Okay, so this is a known result since 17 Edmonds. Define this polyhedron. It's called the polymatroid if h is a submodular function. So what is the set? It's an n-dimensional polytope. You have a constraint for every subset, and every constraint has the evaluation of the function on the right-hand side, and left-hand side is just some of the variables in that set. Okay, so you have 2 to the n constraints like this. So it has too many constraints, exponential number of constraints, but that is your polyhedron. Okay. And it turns out any pi that belongs to this polymatroid gives you a valid inequality for the convex lower envelope. And this is a very simple result from polarity. It follows from polarity. And this is true for any function, any set function, not just for some modular functions. The validity is true in general. So it doesn't give you everything, but it gives you some. It gives you an outer approximation. So this can be used for any set function. Okay? I don't think this is well known. But for the submodular case, it is exact. For the so that was Edmund's result. That gives a convex lower envelope. That's a complete description. Which means that this nonlinear optimization problem can be equivalently stated as a linear optimization problem using exponentially many linear inequalities. They're equivalent. Okay? And it turns out also that the separation problem is easy. It's a greedy algorithm. You can maximize the function over polymatroid easily and find the pi that is violated. Hence, this linear program problem can be solved in polynomial time. That's great. And actually, we use this approach for the problem that I just showed you. If you use these polymatroid inequalities, you essentially solve these problems to optimality, which we couldn't solve before, in very, very short time. I mean, you see here that by adding only a small number of inequalities, so we're not really talking about thousands of inequalities, we're not enumerating all pseudo 100 possibilities, just a handful of inequalities do the job. Those are the ones that are needed. Those are the right ones to add. And you see these are the gaps, these are the original gaps. We were in 2 digits here in some of these. They're very, very small now. And because the gaps are very small, you have a very tight relaxation. This gap is only due to the knapsack constraint you have. If you didn't have that constraint, you would have 0 gap because the problem is in linear program. Because of that knapsack constraint, you have a little more gap. And then we do a little more enumeration. And so these are the times in seconds. You see there's huge improvement in solution times. So this is a toy problem, right? It's a toy problem. And I want to show you its application for a real problem. I don't have time to go over all the details. Mark Daskin at Michigan IE department, he was the department chair until recently there. And some of his students worked on variations of this facility location problem. Here, xi represents whether you open a facility or not. Okay, there's a fixed cost associated with it. And you need to meet the demand of your clients, and then you can only send from I to J to client if you open the facility I. So those are the standard facility location problems. They've added inventory constraints to this problem. There's an inventory cost, there's an EOQ model, economic order quantity model, in case you're familiar with it, but otherwise it's not that important. And there are constraints on sort of capacity constraints. The inventory that you order has to be less than the capacity, and then there's an additional lead inventory that you need to have a safety stock depending on the lead time for the deliveries to arrive to your warehouse, and there's the safety stock part. But you see that square root appears here that for the safety, and also in the objective. So this problem can be cast into this sort of submodular optimization form, and all those sort of polymetric inequalities can be added in this problem as well. What they had done before is they come up with sort of ad hoc column generation, cut generation heuristics, sort of various algorithms, but what we're proposing to do is you don't need any. You don't need to devise special algorithms. Use an off-the-shelf solver, but add these inequalities in there, and you can solve the problems much better. So it is their data set. These are the results they had, and the conic formulation is the sort of new result that we have. There are a few cases where they could not solve it optimally. They thought they were optimal, but it turns out they're not optimal. We were able to find slightly better results. That's not the important point. The important point is that if you look at times, that order of magnitude faster. Okay. And you don't need specialized algorithms. That's the whole point. Right? This is a generic way of looking at these problems. Once you identify that structure, automatically add those polymetric inequalities. It will give you much better. This was done with a joint student with Max, who is now an assistant professor at Purdue School. Now, this is all good. Now that I have so 15 minutes left. It's 1 hour, right? Is that true? Or 50 minutes?
1 hour is fine.
Okay. This is the real part that I want to talk about. So the mixed integer case, which is much more interesting. Often, these optimization problems over binaries, yes, there we have pure binary problems, but my experience is that most practical problems have continuous variables in there as well. So it's not just binary. Right? You have binary and continuous variables. And so because of that, we'll try to address this set. So the new variables, continuous variables here, and non-negative variables, and we're going to introduce this term here. Since the variables are continuous, I cannot write in here y. I have to write y squared. Otherwise, that wouldn't be the standard deviation, right? Now, the challenge here is that this function, g of x is binary, y is continuous. So it is concave in x, convex in y. Okay? I can't directly use the results that we had before. And the convex hull, or the lower envelope, lower convex envelope, is not polyhedral anymore. It has these sort of curved edges, and you can't just use linear inequalities to describe it. You need nonlinear inequalities to be able to describe it. It's just it appears to be significantly more difficult. And I have been trying to solve this problem 10 years, and to try to get an answer to how can I make use of this. We understand it by all pure binary case. How can we do the continuous case? And with a former student, we wrote a short paper in OR letters, gave us some new inequalities, but didn't do the job. And you can optimize G. Even though it's like concave in x, convex in y, it can be solved polynomial time. You can minimize this function in polynomial time, or any C and D. So it is an easy problem in that sense. So we should be able to do a better job. Okay? And I think we sort of finally have sort of an answer to it. So yeah, we have a technical report on this, not published yet. All right, so here's what we're going to do. So that is the set that we're trying to get inequalities to. Right? So without the continuous part, we know everything. What we'll do is go to a higher dimension. Going to higher dimension seems to be working very well all the time. So introduce this new variable, s. Okay? We'll stick here s squared. Now this is conic quadratic. And where s is greater than or equal to square root of c transpose x. So if you eliminate s, you get the original set. Now, if I write it this way, this part is all x. So if I go to this higher dimension, then I can just add all the polymetric inequalities I know on the x part, right? And I have that nonlinear component here. That's fine. And I can use everything that I know for the x case. So if you want, you can get rid of the s variable and then write the inequalities this way. This is a second order column constraint. But with the implementation, you can do it directly using linear inequalities with one nonlinear inequality down there. Okay. That works very well. And it turns out that gives you the convex hull. That is the convex hull. These are the inequalities that you need. You don't need anything else. It can be separated the same way as before. one caveat. Maybe I was too quick. Here we're assuming that y, the continuous variables don't have an upper bound. They only have a lower bound 0. If they have upper bounds, the problem is more challenging. So we don't know the context of that. And we know that it's not this, that there's more. Okay.
But it is still trying to find the convex hull of points in a convex set. You're just adding these linear inequalities to your cone constraint.
Yes, yes, yes. It's still easily solved. It's polysolvable.
Okay.
But this is not. You need to have more.
Sure.
You need to have more. That's what I'm trying to say. Okay. So I'll show you what one needs. Okay. 10 minutes. So this is more or less a real problem that comes up in finance and in other contexts as well. Often we need these binary variables as indicators, whether you do something or not, whether you invest in IBM or not. So Y may be representing how much you invest in IBM stock, but X will denote whether you invested in or not. It appears in facility location as well. So whether you open a facility or not, is this your XI variable, and Y will represent how much you send from facility I to customer J. Let's say Amazon facility I to customer J. So Y's are your fractional variables, and X's are these sort of indicators that are counting the number of open facilities or the number of stocks that you own. These indicators. That's the typical use case. And your objective is typically on the Y variables. Could be some X's as well, but the nonlinearity is typically on the continuous variables. So this can be solved in n squared time. This optimization problem, easy to solve. So we should do a good job in understanding its convex hull as well. If I fix my x variables to 1, then there's a problem in y, and it's a convex optimization problem. Easy. If I fix my y variables to x, then I made y's binary as well. Then it's also an easy problem. It's a submodular minimization problem. We understand this convex hull very well. So how are we going to deal with the case where y is strictly between 0 and 1? Again, so to motivate, to see how difficult it is, here this problem, so this is the recent table, the recent version of Cplex. The Cplex number of variables are larger here, 100 to 500. Your confidence levels here, second column, you see you have still large gaps, and we had 2 hours time limit. We couldn't solve most of these problems. So each row is an average of 5 different instances, and you see that except for one case, none of them could be solved to optimality. And at the end, after doing this thousands of branching enumeration, you look at the end gap that is left between the best upper bound and best lower bound. That is almost the same as the one that you started with. So you've essentially done nothing, right? You haven't been able to improve the bounds. So they are really, really very nasty. If you just throw it to Cplex like that. Okay. So here's our idea. Well, we know the case when x is binary, so we'll fix y to x, and that is the value inequality that we have for the binary case. Good. And then we'll lift those variables. So that inequality is only in x. We're going to write another inequality where it's almost like that, pi x less than or equal to z, but on the right-hand side we will add these additional terms here. So note that the coefficients here is alpha, it is a non-negative. And when x equal to y, that disappears. You have the original constraint. When that is not the case, it's a relaxation of the polynomial inequality. You add something more to the right-hand side. And nice thing is that these coefficients, you can write explicitly. There's a formula to write it. You don't need to do computation to get these coefficients. It's not like lifting. It is sort of a lifting argument to prove it, but you can explicitly state what they are. It doesn't happen in most of the cases, but it happens in this case that we know exactly what they are, and they are quite tight. They're good inequalities in that sense. There are many integer solutions, exponentially many integer points on these faces. These are linear inequalities. Okay? So that's a good case. That's class 1, inequality class 1. We can generalize these inequalities by applying this trick not only on the set n, but on subsets of n. Okay, so you say, okay, I'm going to split my variables n into s and n minus s. Okay? And apply this polymetric inequalities on the subset s, on this part. Okay? And leave the others as is, intact. Don't touch them. Apply the inequalities on some subset. And if you do that, you get these inequalities. So this part just looks like the previous one, and then you have these intact. Now remember, the linear inequalities, for every permutation, we have an inequality. So you have n factorial linear inequality there. And you add the S set, which are taking subsets here, and it's a much richer set now. Right? They're much richer inequalities, and they're nonlinear. These are nonlinear inequalities. And finally, we'll go, this is class 2. We have one more class. We'll introduce another set, T. And so we'll split n into S, T, and then whatever is left, n minus S, T. Okay. On the ST side, from that sort of the inequalities that I mentioned that didn't do a good job, we use those inequalities in here for the mixed integer case and eliminate these auxiliary variables t, and you end up getting this third class of inequality that has s, t, and the rest. So that's the third class of inequality, and this is the most general one. Okay? So if you take t equal to empty set, you get the second class. If you take s equal to empty set, you get, I'm sorry, if you take s equal to n, you get the original linear inequalities. Right? So we have this hierarchy of inequalities, richer and getting so that they're nonlinear and subsuming the previous class. Okay? So 3 classes of inequalities. Okay, let's use them. So same problems that we were trying to solve. Original computations. These are the new computations. No enumeration necessary. We solved every one of them, which could not be solved in 2 hours, at the root node. No branching was needed. Okay. Unfortunately, it doesn't give the convex solve. So these 3 classes of inequalities, even though it's pretty rich, it works very well in practice. We know it does not give the convex solve. Okay. But it works very well in practice. We do add thousands of inequalities in these cases, and we use nonlinear inequalities as well as some of the nonlinear inequalities. But the results are really very good. Solve them at the root node, no branching necessary. Again, this is a very simple toy problem. There are no constraints. I have a couple of minutes, I'm almost done. If you add the cardinality constraint, which is typically used in practice, so you cannot invest, let's say your universe is Russell 3000, you can only invest in 100 securities in it. Your universe is global ag, which has 20,000 bonds in it, you can only invest in 100, 200 or so. That is the cardinality constraint you have. When you add that, we haven't studied that part, right? We only studied the objective function. The results are still very, very good. We don't kill them at the root node, right? We still have to do a little bit branching, but we nevertheless can solve them much, much, much better. And finally, this is the last part, covariance matrix where you have correlations. So far, I've ignored all the correlations. I assume that you have a diagonal covariance matrix, which is an oversimplification of reality. So what happens if you have correlations? Okay. Now your problem changes this way. So sigma is your covariance matrix. So what we'll do, we'll decompose sigma into two parts, the diagonal and the sort of factor part, low rank factor part. In practice, in high dimensions, the data comes this way anyway, right? One uses factor models. You wouldn't, if you have, let's say, 3,000 stocks, you wouldn't generate from sample 3,000 by 3,000 covariance matrix. So you will have some model generated covariance matrix, which will have is the residual component D and the factor component, low rank factor component. So data comes this way anyway. So what we'll do, we'll split that matrix into two and move the factor component to the constraints. And now look at the objective. Objective is again diagonal with this conditional variable S. And I can apply all the results that we know on this set. Okay. Essentially what we're doing, you have a general covariance matrix, apply the results on the diagonal part. You can do that. It is because it gives you relaxation. You're able to write it as in a relaxed way. And that's what we do. And the results with the correlated matrices is that, again, huge improvement in solution times. These are the smaller ones which could not be solved. Now they're solved in a few sort of seconds. These larger ones, some of them we could not solve to optimality with zero gap, but look at the end gaps. They are very, very small, 0.2, like 20 basis points for all practical purposes. This is good. All right. So last slide is, I hope I was able to convince you that this type of utility function arises sort of often whenever you're modeling uncertainty in combinatorial problems. We have limited capabilities in off-the-shelf solver to be able to tackle these problems, and we do need to exploit sort of special structure and somehow add that into these solvers. I think, to me at least, the biggest challenge is identifying that special structure that is not overly simplistic that you can utilize for more general problems, but nevertheless that's chewable, that you can get results. Right? If you go too general, it just becomes computationally very difficult to deal. Also, two things that are very difficult to do, but you don't want to oversimplify things that so you cannot apply the results to the real problem. But just finding that right balance is, I think, continuing to be a challenge. Thank you very much.
Maybe we have time for a quick question.
How about a quick naive question?
Okay, yeah.
This is very interesting. I hope it's also not a digression. Maybe it's all very well known, so it applies to all of your problems. Suppose you get all of this, I appreciate the nuance, but now you change the parameter a little bit. Will they jump the optimal solution?
If you change the parameter, what?
So like you said A or C, that's how you began your talk. So suppose I change A a little bit. Will the
yeah, the solution may change.
You see, the reason what I'm trying to get is that argmax correspondence be somehow continuous, some such in some. No, that's my.
Discrete problems, yeah, definitely. So it may just, the solution may just be far away from, quite far away. In the continuous convex case, you have this nice problem, but not in discrete problems, unfortunately. Maybe you know more about this.
No, I mean, yeah, that's pretty much true.
I think this is why economists. I mean for the theoretical investigations.
Right. Yeah. I mean, these continuity or differentiability properties of these things are to establish. Okay. Let's thank Alper again. And we do have refreshments in 301. And you can ask Alper more questions at that time.